Okay, so what we're going to talk about here is Kirchhoff's current law and Kirchhoff's voltage law. First, the current law. Basically, the Kirchhoff's current law states that the algebraic sum of currents entering and leaving any point in a circuit must equal zero. So if I have a circuit that branches off into a couple different branches, or if I have a circuit that has a couple different branches that combine, that junction where they basically divert or combine, the current going into that point must equal the current going out of it. So let's look at some pictures or examples that'll help communicate that to you. So if I take a look at this slide and I go to the next slide here, you can see that I've got three branches here. I've got 5 milliamps, 10 milliamps, and 15 milliamps. And they're all combining, all three of these are combining into this point, and they're separating as a single current. So basically, all three of these have to basically add up and equal the current that's on the other side. So you can kind of think about it as an equation. If you think about the junction point as the equal sign, what's on the left side must equal what's on the right side. So I've got 5 plus 10 plus 15, all that equals 30. If you set it up that way and think about it that way, it might be a little bit easier, okay? Looking at another example, we also have the opposite case where I'm looking at this current here and it comes into this point and it's going to separate. Now, the actual amount that it would separate is going to depend upon the resistor values, and we'll talk about that a little bit later in another video. But if you take a look at this current here, 30 milliamps, goes to this point, it separates, and because these resistors are equal, the currents are also equal. So I've got 10 plus 10 plus 10, okay? Kirchhoff's current law here, if you take a look at this, you can see this here is another good picture showing you how this is going to work. So that red circle is basically where the equal sign is going to be. All the current that is going through this 10 ohm resistor is going to separate. Some of it's going to go through the 15 ohm resistor, some of it's going to go through the 20 ohm resistor. Now, looking at this picture here, you should be able to see which resistor is going to get more current. Basically, the lower resistance is going to allow more current to pass through. So this 10 ohm resistor, most of the current's going to go through the lower resistor and some of it's going to go through the 20 ohm resistor, okay? So remember, branches that have smaller resistance values are going to have more current because it's resisting less, okay? This one here, same thing. You can see how the numbers actually are changing there. We can look at the ratios of the resistors to figure that out. And that's basically what this equation is here, okay? So if I take a look at this equation, I'm trying to figure out how much current is going to go through the second one. I'm going to take the total current, and this is the initial current. This here, this value is basically a ratio where I'm taking the values here in the resistors and using that to figure out my ratio. My denominator is going to be both of the resistors added together, and the resistor that's in the numerator is going to be the opposite resistor of the branch I'm traveling in. So if you take a look at the I2, I put the R3 in the numerator. So I put the total in the denominator, and I put the opposite one in the numerator, and that's going to give me the ratio to multiply to figure out how much current applies. Okay? Looking at Kirchhoff's voltage law, this is basically saying that the algebraic sum of all the voltages around the closed path is equal to zero. So if I take a look at this circuit, I've got several resistors going through here. And I can actually look and see that my voltage is supplied by my battery here, 10 volts. And as I go through a resistor, some of that voltage drops away. If I look at all the voltage that's here, if I add this up, I've got positive 10 here -2, -2, -2, -2, -2. The reason why it's positive for the battery is because it's being supplied at that point and it's being absorbed by the resistors. That's why it's negative. So basically, if I look at any closed loop, I can see that it's going to end up being 0. +10, -2, -2, -2, -2, -2. Same example over here, okay? That's going to also give me that information. Now, if I look at multiple loops, this is a little confusing here. If I take a look at multiple loops, this circuit that's drawn, if you imagine the circuit without any X's or O's, the entire circuit has 2 branches. It's got the voltage supply, it's got this branch here that has a single 100 ohm resistor, and it's got this branch that has 2 resistors in series, okay? So if I'm looking at Kirchhoff's voltage law, I'm going to basically use my hand to cover up or X out those 2 that are in the second loop and just look at this loop here. You see, that's 1 loop. So that means that this voltage supply, if it's 10 volts, that means that this voltage is going to also be 10 volts, okay? Looking at this picture here, you'll see that if, again, I have 10 volts and I'm going to ignore this here, that way I have a complete loop here, this is 10 volts, and that means that the sum of these 2 voltage drops is also going to be 10 volts. Now, knowing that the resistors are equal, I'll know that each one will be 5. So I've got V, the supply is 10, -5, -5, and I get back to 0, okay? Now, when we setting up our circuit problems, we need to make sure that we're going to have a chart because we're going to find voltage, current, and resistance for every resistor that's in our problem. So we want to make sure that we set up a chart and have that handy. And in the chart, I always like to list it the same way that it's listed in Ohm's law, V = IR. And then we go ahead and put our units up at the top. That way we don't have to carry them through the entire chart. That helps to organize it. It makes it nice and neat and easy to follow.